Hello alchemists, and welcome to another short video lesson for our wonderful Chemistry 182 class. Today we're going to talk about standard enthalpies of formation, which is yet another technique that we can use when we're in our cabin in the woods and our boss calls us to say, hey, I need the enthalpy change of this particular reaction right away. I don't care that you're on holidays. And again, fortunately, your chemistry library involves another set of data booklets with lists of standard enthalpies of formation for a variety of different compounds. So, yes, Carrie's rambling again. But in our data booklets, we can use these values, again, obtained through numerous experiments, averaged, correlated, verified, yada, 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 put in print in our data booklet for us to use. Now, previously, we were looking at, with our Hess's law, we would look at a mini reaction, something like this, and we would use the enthalpy change of that chemical reaction. Maybe this one is negative 36 kilojoules, something like that. We would use that information in conjunction with other mini reactions. Maybe we've got D plus B, A plus C, something like that. And our delta H for this one would be plus 18 kilojoules. So with Hess's law, the amount of energy that is released in the Ford's reaction is 36 kilojoules. For the second one, we require 18 kilojoules of energy for the Ford's reaction. The idea with Hess's law is that if we take everything that is required in each reaction in terms of our chemical entities and the net enthalpy change of each of those, to create a net reaction as well. So for example, I know you've done Hess's law already, so just really quickly, the A's can cancel, but that's it. When we have our B's on the same side, they add up, C's on the same side, add up like that, and we get our net equation down here. So in this case, for example, D plus 2B, or not to be, sorry, is at equilibrium with 2C. And our delta H is the sum of these two reactions, in this case, which would be negative 18 kilojoules, because Carrie picks numbers that are easy for her to do quickly. Good so far? So just a quick recap of Hess's law. But what we do with standard molar enthalpies of formation is, instead of looking at an entire mini reaction like we have here and its net enthalpy change, what we would do with standard molar enthalpies of formation is look at how much energy is locked up in each one of these. So we're kind of looking more at the potential energy that's stored in each one of these different chemical entities and determining the overall enthalpy of equation based on the difference between the reactants and the products. So that's our task today. That's our standard molar enthalpies of formation method. And let's have just a quick look at some of the basics before we get an example. So 11.5, in case you're reading along with your textbooks, she chuckles. Anyways, 11.5, standard enthalpies of formation. Now, the very first statement here is super duper important. It says, by convention, the natural state of elements at SATP is often used as a reference energy state. So essentially what we're going to do is take that as our baseline and compare everything to our elements. That's an E. There we go. So if it has more potential energy than an element, we're going to call it positive. If it has less potential energy than an element, we're going to call it negative, and that's in terms of its energies. In order to make the baseline easier, we're going to give the potential energy of the element a state of 0 joules. Okay, so 0 amount of energy. Now, it doesn't have zero. It's just a relative reference point so that we can make our little table and say some things are positive. In the middle, we have elements. And if it's less than an element, we call it negative. So again, just a baseline, not an actual zero. For our calculations, however, we will be able to use it as zero, which makes elements our new favorite thing because it makes our math even easier. Okay, just as a sort of a rough analogy for you here, it says, similarly, water freezes at 0 degrees Celsius, but that does not mean it contains no heat or kinetic energy. If it was 0 Kelvin, that would be a different story. But 0 degrees Celsius, water freezes. We know that water as a solid still has energy in its bonds. Okay? So just a rough analogy to compare that. Using this convention, and that is the whole relative reference point of elements, the enthalpy change of formation reactions can be calculated and communicated in tables. So it says to see Appendix 1 of our text or our data booklet, and I've got the images from our data booklet coming soon. Such tables can be used with Hess's law to more easily determine the standard enthalpies of many reactions. So we can use Hess's law and this method of standard enthalpy of formation for a single reaction to find something completely unusual. For example, one of those highly radioactive or expensive chemicals that we can't use in class or in the lab, we could definitely create an enthalpy reaction and figure out how much energy it should theoretically take. Okay, so I'll just read that last one again. Such tables can be used with Hess's law to more easily determine the standard enthalpies of many reactions. They can also be used to determine the enthalpy of reaction for a single reaction without the need for the mini reactions used in Hess's law. So there's two different ways we can do it. This is the way we're going to focus on now so we get the technique. If we have time later on, I may come back to this and discuss this a little bit. But this is what we're going to focus on, just calculating the enthalpy of reaction for a single reaction. All right, here, excuse me, here are those data tables from your data booklet. And don't let the numbers at the bottom of the page fool you. These are actually on page 7 and page 8 in our data booklet. That is an 8, believe it or not. So I'm just going to cross this off. So just having a look at these tables, it says at the top, standard molar enthalpies of formation at 298.15 Kelvin. So we're working at SATP conditions. And we have a list in alphabetical order of just some of the more common compounds. Okay, so definitely not an inclusive list for sure, but it is some of the more common compounds. I'm going to cough, excuse me. Excuse me. All right, so if it is happening at SATP under standard conditions, then we know that the states of these compounds will be in their SATP state. But fortunately for us, the data booklet lists that as well. So for example, aluminium oxide at the top here is a solid in its natural state at SATP. And so this value here, the 1,675.7 kilojoules per mole, is how much energy it takes to create 1 mole of aluminium oxide in its solid state. So you can see that mostly these guys are negative. So formation reactions tend to be negative. So when we bring things together and create a bond, it actually releases energy as those things combine. Some of the exceptions are some of our higher energy compounds or complex compounds such as benzene. So benzene takes 49.1 kilojoules of energy per mole of benzene to create that bizarre ring structure. Okay, so there's a few positives, but mostly negative. And the other thing I want to point out on this table before we move on is that over here we've got water just in 2 states, not in 3 states, but in its liquid and vapor forms. And the values for those over here, we have liquid and we have gas. Now it may seem slightly counterintuitive here when we look at the values for those energies per mole. Water, for example, 285.8. Water vapor, on the other hand, 241.8. So if you think about what's happening though, this is a formation reaction. So when we're making liquid water, we release more energy. Liquid water is at a lower energy state. When we make water vapor is higher energy. So it's actually going to give off less energy, 241.8 kilojoules per mole. Give off less because it's keeping more energy in itself, okay, at that higher energy state. So just be careful when you're dealing with water, because they will be very different depending on the state of matter that it's in. Okay, we'll keep coming back to this table for the rest of the video, so you will be familiar with it soon. We're going to do the thing where we kind of learn how this process goes along with a concrete example. It says, what is the standard enthalpy of reaction for the reaction of gaseous carbon monoxide with oxygen to form gaseous carbon dioxide? Good old word equation there for us. The first thing we have to do is write this balanced equation. So the reaction of carbon monoxide, CO, G, with oxygen, O2, to form, and Chem 30, CO2. Now, a couple different ways that we can balance this. I can hear people screaming, don't you dare use a fraction. I can hear others screaming, but it's so easy if you use a fraction. We're not going to use a fraction just for fun right now. For example, I'm going to balance it like this. So I've got 2 carbons, which means I need a 2 over here, 2 carbons. Now I have 4 oxygens, 1, 2, 3, 4 oxygens. I'm good to go. So molar ratio 2 to 1 to 2. People screaming in the background, you can also do it to 1, 1/2 to 1. And we'll see why, hey, fractions are sometimes a little bit nicer to deal with these types of questions, but for now, no spoilers. All right, so here's our balanced equation. Second step is to use the table to find the standard enthalpies of formation for each reactant and product. So if I look at our table, I'm going to get these standard molar enthalpies of formation for each one of my chemicals that I have in my equation, so carbon monoxide, oxygen gas, and CO2. So I'm going to go back to my table. As soon as I find my table, there we go. Excuse me. So first of all, carbon monoxide. So carbon monoxide is here at 110.5 kilojoules per mole exothermic. And while I'm here, I'm going to grab carbon dioxide immediately above it, CO2, which is negative 393.5 kilojoules of energy. So it releases a lot more. Excuse me. All right. You'll notice I didn't look up oxygen on our table. And I didn't do that because oxygen is an element in its natural state, which means it is, hooray, 0 joules of energy, 0 kilojoules per mole. So that makes it nice for us when we have an element in its natural state, it's going to be 0. That means we're not going to have to do anything else with it in terms of its calculation. All right, so carbon monoxide was negative 110.5 kilojoules per mole. And carbon dioxide was negative 393.5 kilojoules per mole. And I have a data table open in front of my very eyes. There's no way I would have remembered that from slide to slide otherwise. Okay, so there we go. I've looked them up in the table. And now I'm ready for step 3. I'm just going to, where can I put that? I'm going to write it up top here. Just write our balanced equation down again. So we can refer to that. So step 3 says find the enthalpy change of formation. Wow, that's just a seamless copy paste there. Find the enthalpy change of formation for all reactants and products, taking into account the number of moles. So really what this means is that we're going to find the delta H of formation using delta H equals NH. And both of those H's get the subscript F for formation. Now I'm only going to write the formula down once because I'm quite lazy. That's totally fine to do. And then for each one of these, I'm going to just do this. And down here, do that. Now, carbon monoxide has 2 moles. So I'm going to take 2 moles and multiply it by my negative 110.5 kilojoules per mole. And I can see my moles cancel, and that's what's going to give me my enthalpy change value in kilojoules. So that will be negative 221.0 kilojoules. Oxygen is 0, so I can ignore it. But carbon dioxide is 2 moles as well. So negative 393.5 kilojoules per mole. And I would do that one in my head, but I'm worried about making a mistake in my video. So quickly calculated that, 787.0 kilojoules. Just a little note, O2 gas is 0 kilojoules, just in case we get there and we're like, what the heck? What's going on there? Now I'm just also going to separate this into reactants on the left, products on the right. Our reaction does that for us, but down here as well, I've got reactants here. And products down here. And the reason I'm doing that up here is just to get us ready for step 4 here. So step the 4th, apparently. The change in enthalpy is equal to the heats of formation of the products minus the heats of formation of the reactants. So if you want to think of this in terms of any sort of delta, this is final minus initial. In our case, final is the products. Initial are our reactants. There we go. Products minus reactants, okay? The formula is written over here for us. Now this delta H is an R for reaction, because we can use it for a whole number of different types of reactions. So just generic. And this delta H R is for our original equation, our balanced equation that we want to find the delta H for. So this is our whole purpose, is to find the enthalpy change of this unknown reaction using the enthalpy bound up in each reactant and product, okay? All right, so let's give this one a try. I'm going to switch back to yellow. It's a little easier to see on the screen. So our delta H is the sum of our products minus the sum of our reactants. Because we've already calculated out the enthalpies of formation, we could also write it like this: delta H of formation of our products minus the sum of the delta H of formation of our reactants. What I would recommend that you do, because there's going to be some negative signs and a subtraction sign, and sometimes things get a little funky, I'm going to do a big old product bracket minus a big old reactant bracket like this. In this case, it's not too bad. I only have 2 reactants, one of which is 0, and 1 product. But later on, when you have 2 or 3 reactants, it gets a little bit, as I say, the word of the day is funky. So products. Products are, in this case, on the right-hand side, the carbon dioxide. So our carbon dioxide value is negative 787.0 kilojoules per mole. I'm going to pop that in this big old bracket. So there's my product. Oh, did I say per mole? Just kilojoules now, just kilojoules. All right, and then minus, that's our algebra sign, our minus. And then our next set of brackets here for our reactants. Our reactants on the left-hand side, of course, in this case are carbon monoxide and oxygen. Carbon monoxide, our total is negative 221.0 kilojoules. And oxygen. So it's the sum of the delta H formation of our reactants. So that's why I put a little plus sign there. It is 0. It doesn't matter. We all know that, but I'm putting it in anyways. So this time, you've got negative 787 minus negative 221. So that's plus 221. Gives us, oops, that's an equal sign, negative 566.0 kilojoules. Again, to 1 decimal place because it's subtraction and we're preserving our precision level there. Okay, final answer. We've already done our siggy diggies, so that is our final answer. 566.0 kilojoules of energy for this reaction. Excuse me. Now, if I go back up in terms of our slides, what have we done, people? What we've done is we found the enthalpy change here for this reaction. Negative 566.0 kilojoules of energy. That's what we've discovered. And we did that by essentially saying how much energy is stored in our reactants, how much energy do we end up with in our products. The difference between them is our enthalpy change. That's essentially what we're saying. I'm going to say it one more time. The energy total of our reactants and the energy total of our products. We take the difference between the left and the right-hand side, the difference in the energy, and that's the enthalpy change of our reaction. What we're seeing here with a negative sign is that when carbon monoxide and oxygen gas combine, they're going to release 566 kilojoules of energy for this reaction here. Groovy? I hope so. What we're going to do is do it again. I know. This slide, I'll read it through it quickly with you. It says, note that this is the same result as adding the equations as previously shown. So Hess's law, but with less manipulation. So we could have another way to do this type of question, and I'm just going to quickly, here we go, oh no, I'm going to quickly write it down incorrectly. Don't worry, I'll correct that. Hang on. Oh, I just have to take out that. All right, so here's our reaction, and we have balanced it. We could have used this and Hess's law by creating formation reactions for each entity. So I could have said carbon plus oxygen gas makes carbon monoxide. And the delta H on the table, from our data table, page 7 and 8, is negative 110.5 kilojoules per mole of energy. Okay, now this one isn't balanced. I could do that with a fraction here, excuse me, or with whole numbers. If I do it with a fraction here, then it's just 1 mole of everything. So I think I'll do that this time. And then this changes it, because it's 1 mole, this changes it to just kilojoules like that. And then I could write the other entity here. Now, oxygen gas does not get a formation reaction. It's just an element. But I could write a formation reaction for this guy here. I could also write carbon, same substances, right? Plus oxygen gas makes carbon dioxide like this. And the delta H for this one, negative 393.5 kilojoules per mole. Now if I balance this one, one carbon, two oxygens, pardon me, fantastic news, it's already balanced. So that is for 1 mole of carbon dioxide. So our delta change for the reaction as it's written is just negative 393.5 kilojoules. So I can take that per mole away. Then I could do the whole Hess's law thing with this. I could add these up according to Hess's law to get our net equation here. I would have to reverse this one because my carbon monoxide's on the wrong side. So if I reverse this one, I know, let's go left. I get carbon monoxide, carbon solid, plus 1/2 O2. And now my delta H here would become plus 110.5 kilojoules. The other thing I would have to do, I'm just going to make this a little neater here, because I'm sure your eyes are bleeding as you're watching this. So I've had to reverse this. The other thing is that in my reaction up here, I have 2 of each of these gases. So carbon monoxide, carbon dioxide, I have 2 of them. So I'm going to have to also times this by 2. So times 2 in reverse. So I just times 2, and 1/2 becomes just 1. And then my delta H I also have to times by 2. So 110.5 kilojoules now becomes, before your very eyes, 1.0 kilojoules. We look at our second reaction. Our second reaction, carbon dioxide is a product, carbon dioxide is a product, so that's good. I just have to multiply this one by 2. And so I'm going to multiply by 2 over here on the left. 2O2. Pretend my arrows line up perfectly here, guys. And 2 carbon dioxides. Of course, I also have to double my delta H. So my delta H becomes negative, what was it, 787.0 kilojoules. So with Hess's law, I now would proceed to cancel everything out that I can. So 2 carbon solids are gone. Oxygen here cancels, releases this or reduces it down to 1, and everything else is as is. So when I bring it down, I have 2 carbon monoxides making, oh, pardon me, ha ha ha. These are not the droids you're looking for. Okay, I missed this guy here. So 2 carbon monoxides plus an oxygen gas makes 2 carbon dioxides, and our delta H, we would add these guys up. So 221, 787 negative, and we would get negative 566.0 kilojoules. So we did the exact same question, but we did it in a lot longer of a method. We created our Hess's law mini equations in yellow and white here. They were formation reactions because those are the enthalpy changes that we had available to us. So we wrote the formation reaction, looked up the value, wrote the formation reaction, looked up the value, then we manipulated a la Hess, and then did our canceling, adding up, and we ended up with this net equation. Now that net equation is exactly the same as this net equation, and we found the delta R for this reaction using standard molar enthalpy of formation method and got the same darn value. Both are totally valid. It's just that this method, believe it or not, this method here where we balance the equation, look up the enthalpies, multiply by number of moles in our equation, and subtract products from reactants from the products to get that value. It is much, much quicker. We will do another example from scratch. And I'm going to show you what's called the table method to solve for this. Some people like this. Some people like to organize things their own way. It doesn't matter as long as it's totally clear. So this one says calculate the change in enthalpy for the incomplete combustion of benzene. Remember, incomplete means making carbon monoxide. But we don't even have to do any work, right? Because the balanced equation is given to us in this case. So that's fantastic. The table method is to just essentially lay everything out underneath. So I'm going to look up the molar enthalpy of formation for each one of these entities, and I'm just going to list it underneath. So for example, benzene, I have to look it up. I'm looking, 49.1, so plus 49.1 kilojoules per mole. Oxygen, what's oxygen, you guys? Why am I switching to my red pen? That's right, it's an element in its natural state, so it's just 0. I'm just assuming that you all were screaming at this screen with joy that you remembered that it was an element in its natural state. So the benchmark makes that 0. All right, next one is carbon monoxide. Well, we just use carbon monoxide, so hopefully I remember that one. Negative 110.5 kilojoules per mole. And the last one there is water. Caution, caution. Make sure you check the sign. And this one, water vapor, has an enthalpy of formation of negative 241.8 kilojoules per mole. All right, so I've looked everything up. Now I'm going to calculate the delta H of formation for each one of these based on the number of moles in my balanced equation. Okay? So number of moles in my balanced equation in this initial formula. I've written it once. I'm not going to do it again. I'm lazy. But I am going to do it for each one of them. I'm going to write 2 moles for benzene times 49.1 kilojoules per mole. And that's going to give me 98.2 kilojoules with my moles canceling. I'm going to bring this one joyously down, 0. My carbon monoxide, this one, good grief, 12 moles. 12 moles of carbon monoxide times negative 110.5 kilojoules per mole. My moles are going to cancel. Excuse me. And I'm just going to use the calculator for this one. And I'm going to get 1326 kilojoules. And that is exothermic. Oops, I forgot to put my plus sign. Oop, minus a half for Carrie. All right. And then finally, my water vapor, for this one I have 6 moles times my negative 241.8 kilojoules per mole. Moles cancel. And that leaves me 6 times 241.8 equals negative 1450.8 kilojoules. All right. There we go. So I've got all of my setup done. I'm going to dramatically remind myself which are products and which are reactants with my amazing slithery blue line here. And then for down below, I'm going to write out my formula, the delta H of the reaction, and that is the delta H of this reaction up here. This is what we're solving for. It's going to be equal to the sum of delta H reaction products minus delta H reaction reactants. I'm giggling a little bit because I don't know if you can hear it, but in the background someone has just turned music on. So we may have a soundtrack for the rest of this video. Okay, so I'm going to do my products and reactants brackets here. And in my products and reactants brackets, I'm going to add together my enthalpy values. So products, remember, I have two. I have carbon monoxide, negative 1326 kilojoules, plus, maybe I'll just put these in little separation brackets here, negative 1450.8 kilojoules for my water vapor, it says kilojoules, it's kind of microscopic. And then minus my reactants are 98.2 kilojoules for my benzene, and then plus 0. I'm going to go ahead and do this calculation. 1326 negative plus 1450.8 negative, and then minus the 98.2, and I get 2678.6 kilojoules. They just crank the music too. And that is our delta H of our reaction. So that is the enthalpy for the incomplete combustion of benzene. It makes sense that it's negative. It's a combustion reaction, so it should be releasing a whole ton of energy. This is our delta H, or you can switch that to combustion of benzene if you want. The only thing is that because of our sig digs here being 4 in multiplication event, now our addition subtraction event has to be to the nearest ones place. So our delta H of reaction is going to be negative 2679 kilojoules. All right. Red box of victory because 3, 2, 1. Poof. What? Calculate the enthalpy, change in enthalpy for the incomplete combustion of benzene. What's going on here? You see the difference? This is because of the dichotomy in the room between people who like whole numbers and people who like fractions. Now, if you like fractions, you'll see that this one was easier to balance 9/2 oxygen. Everything else is the same. I won't repeat the entire equation for you, but what you'll find out is that because I'm just going to go back, this reaction was calculated for the combustion of 2 moles of benzene. When we do the entire calculation for this one, it will be for 1 mole of benzene. And the answer we get for our delta H of reaction for this will be exactly half. Let's see if Carrie can do a calculation this time. Which is 1339.5 kilojoules of energy. Or if you do it, the sig digs may vary depending on how they work out with our multiplication, but probably it's going to end up to be 1340 kilojoules if it's the same precision level as the previous example. Okay? So that is essentially how we use standard molar enthalpies of formation. Oops, I didn't want to go there yet. If you feel super duper confident, so there is another example in your notes, and I'm just going to quickly scribble this down. C2H3Cl gas plus H2. So here is another example from your notes, and we want to calculate the delta H of this overall reaction here. This is what we're solving for. A little messier, getting messier. That's a good. That's a good. There's the good. Okay. Now I am going to just quickly look them all up just to make sure, and I've got plus 52.4 kilojoules per mole. I've got minus 92.3 kilojoules per mole. This one I have from a separate data sheet. This one is not in ours, but it is written in your notes as well. So this one is plus 37.2 kilojoules per mole. And this was hydrogen in its elemental state, 0. Okay, so quickly double checking our balance to make sure we're not pulling a fast one on here. 2 carbons, 2 carbons, 1, 2, 3, 4, 5 hydrogens, 1, 2, 3, 4, 5 hydrogens, that's good. 1 chlorine, 1 chlorine. So it's balanced as is, 1 to 1 to 1 to 1. But even if it isn't, you can also use this. This is only if you're feeling very confident with this method. Otherwise, I would recommend you stick with the table method like this, step 1, step 2, and then finally the calculation step 3. Okay? Oh, Carrie's going the wrong way. If you are confident, excuse me, you can say that the delta H of the reaction, that's this guy here, is equal to the sum of the delta H of formation of the products. Yeah, we're skipping a step. Minus the sum of the delta H of formation of the reactants, where delta H equals NH. Of course it does. That's just off to the side somewhere. And then you go ahead and do the same thing. This time, however, your brackets are going to be huge. Actually going to make that one smaller because I only have one product. And essentially, this case, you would just do the calculations all in one step. So for delta H of formation of my products, I have this little beastie here, but only 1 mole. So I'm still going to write 1 mole because I need to have my units cancel. 1 mole times plus 37.2 kilojoules per mole. And then my other product is hydrogen. Moles cancel. And then this set of brackets is for my reactants. So that's C2H4. And again, 1 mole. Okay, this is a bad example when they're all 1 mole. I freely admit that. Oh well. Plus my HCl, 1 mole, times negative 92.3. I'm just going to move that bracket over. Kilojoules per mole. So you can see it's exactly the same thing. We're just doing step 2 and step 3 in one colossal, giant step 2. Okay. That looks like a mustache and an eyeball. Okay, maybe not. This one I actually have written out or solved already. Hallelujah, you don't have to listen to me trying to use my calculator. Anyways, this one works out to plus 77.1 kilojoules of energy. So final delta H of reaction for this one. Everything here works out to 1 decimal place, so we're actually fine as is, plus 70. Oh, stop it. Plus 77.1 kilojoules of energy. Big red box. Victory box. Woo! Okay, and that is how much energy, there we go. That is how much energy that this reaction takes in order to go forward. So it's an endothermic reaction plus 77.1 kilojoules. All right, and that is standard molar enthalpy of formation. If I go back again, the table method nicely lays everything out. Balanced equation, look up your enthalpies of formation, adjust for the balance, the number of moles here, adjust for those number of moles, get our enthalpy of formation for each one. Then we do products first, that's products, minus reactants, okay? Reactants. Like that. All right, hopefully that makes sense. A couple for you to try down below, and email me if you do have any questions. All right, guys, hasta la vista. Ciao, ciao.